Hello, Mr. Long. This is frq number 4. All right. frq number 4 asks us to, for part A, asks us to draw a free body diagram showing all the forces acting on the ball. So the ball has a force of Fn acting diagonal, and then the force is Fg pointing downwards. Okay, part B. Part B asks us to find the Fn exerted by the ball onto the ball in terms of mg, r, and d. Okay, so I'm just gonna draw out the scenario real quick. So this here is gonna be Fn. This is gonna be d, and then with matching Fn, that's gonna be a big R, and then this little piece right here is gonna be R, and then because this here matches with d, this down here would match with y, and then this here entire thing will equal big R. Okay, and then I have my angle here be theta. Okay, so we know that r squared is going to equal to d squared plus r squared. And if we simplify for little r, it should be r is equal to rad r squared minus, or big R squared minus d squared. And that I will use later. Okay, so we know that net force in the y direction is equal to 0. We also know that net force in the y direction is equal to Fny minus Fg. Then we're going to equal those two together. Fny minus Fg is equal to 0. We can open up Fny to F and cosine theta, and then Fg to mg, and then add it over to the other side. And then to isolate for Fn, we divide cosine theta. So Fn is equal to mg all over cosine theta. And then here, since we determine the angle to be here, Fny is the adjacent part of the triangle. So yeah, okay. Part C asks us to prove that a tangential speed can be expressed, but with v is equal to rad g r squared minus y squared all over y. Okay, so we're going to look at net force in the x direction. So we know that net force in the x direction is equal to Fnx, but net force in the x direction is also equal to Fc, which is equal to mv squared over little r. And then this little r because it should be the one that's parallel to the, or like on the same plane as like the movement. Because big R is like pointing like a diagonal upwards. So that has to be little r. Okay, we're going to equal the two together. Fnx is equal to mv squared over little r I mean. And then we're going to break up Fnx into Fn sine theta is equal to mv squared over little r. And then since we found Fn to be mg over cosine theta earlier, we're just going to plug it in for Fn. So mg divided by cosine theta times sine theta is equal to mv squared over little r, and then they both have an m, so that will cancel out. And then sine theta over cosine theta will turn into tangent theta is equal to v squared over little r. And then here, we know that since the angle is here, your tangent would be opposite over adjacent, which is r over d. So we replace tangent theta with g times little r over d is equal to v squared over little r. And then we isolate for v, so g little r squared over d is equal to v squared. And then earlier we found that v or r little r is equal to rad r squared minus d squared. So then r little r squared would just be g times, or little r would just be big R squared minus d squared, and it'd be all over d is equal to v squared, and then we just radicalize both sides, so it'd be rad g times r squared minus d squared all over d is equal to v. And then here, for the function, I couldn't find a way to find the function to be just straight up with y, but the question asks us if it for it for it to be like can, it uses can. So I think the only way for it to be possible where there's y instead of d is if d is equal to y. So you can substitute d with y. But yeah, so if d does equal the distance of d does equal the distance of y, then you could replace it this equation with it. So it'd be v is equal to radical g r squared minus y squared all over y. So that's it. That's in my opinion, that's the only scenario where I could see where the equation v can have y like in this form. Okay. Part D asks us to derive an expression for the ball's angular velocity in terms of r, y, and appropriate fundamental constants. So we know that the general formula for v is equal to r omega. So then to isolate for omega, you just divide r. So b v over r is equal to omega. And then earlier we found v to be this. So I'm just gonna replace v with that times g all over big R squared minus d squared all over d. And then we found that r to be radical big R squared minus d squared. And then it's equal to omega. I'm just gonna rewrite it over here. And then we can put the bottom into the same we combine it with the top because they both have a radical underneath them. So it'd be g all over big R squared minus d squared all over d times big R squared minus d squared, and then those will cancel out, so you're left with omega equaling to radical g over d. Okay. Part E asks us to prove that the omega minimum, is equal to radical r g all over r, or rad big R g all over r. Okay. So earlier we know that we stated that omega rw is equal to, which is equal to v, which is equal to radical g, or wait, let's see. So we know that omega is equal to radical g over d, and for it to be minimum, that means that your d, which is your distance from the below the rim, has to approach big R for it to be minimum, because the minimum in like centripetal movement is like when you're farthest away from your center. So your minimum would just be, you can just replace d with r. So omega min is equal to radical g over r. And then to get to that form, we'll just rationalize. So we'll multiply both sides, or the top and the bottom, I mean, with, or we're just going to rewrite it to be rad g over rad r, big R, and then we multiply the top with rad big R and the bottom with rad big R as well. So we'll get the form of radical r g all over big R. So yeah, okay. Part E? Part F asks us to find omega in terms of RPM if R is equal to 20 and then the ball is halfway up from the bottom of the bowl. Okay. So here, as stated before, we found omega to be radical g over d. And then here we say that r is equal to 0.2, or it's 20 centimeters, which is 0.2 meters. And then, so that means r over 2 is equal to 0.1 meters. And then, since it states that it wants us to find the halfway up the bowl, we can just make d r over 2. So, you know that omega is equal to g all over 0.1, and that would equal to radical 98. And then to convert to, so right now this is in terms of rads per second, and then to convert to RPM, we just multiply it by 60 and then divide it by 2 pi. So you would get 94.533 RPM. Okay. Right. Part G asks us to derive an expression for the period t in terms of the variables given and any appropriate fundamental constants. So we know that omega is equal to 2 pi over t, but we also know that omega, as found earlier, is radical g over d. So we're just going to equal these two together. So you're left with 2 pi over t is equal to radical g over d. And then for multiply t over, so be 2 pi is equal to radical g over dt. And then divide rad g over d to both sides. So be 2 pi times radical d over g is equal to t. But we know that in the image that r is equal to d plus y, or big R is equal to d plus y. So we know that d is equal to big R minus y. So we can replace d with that. So t, or 2 pi times rad big R minus y all over g is equal to t. Okay. Part H, the scenario changes. Is now the ball is now rotating instead of angular speed omega about its axis of symmetry. Okay. And then we find the angular speed needed to keep the ball rotating with the ball stationary relative to the surface of the ball. And then, okay, so we know that net force in the y direction is equal to 0. We also know that net force in the y direction is equal to Fny minus mg. Equal those two together, Fny minus break up mg is equal to 0, and then Fn y is equal to Fn cosine theta is equal to mg. And then here we're given the angle to be down here, so Fny is cosine. Isolate for Fn is equal to mg over cosine theta. Okay. Net force in the x direction is equal to Fnx, which is equal to Fn sine theta. But we also know that net force in the x direction is equal to Fc, which is equal to mv squared over r, or little r, I should say. But then we know that we can break that up into v into m times r squared omega squared divided by r, so you're left with m little r omega squared. Okay. And then here, looking at the triangle we're given, which is similar to the one I drew earlier, we know that sine theta is equal to little r over big R. And then to isolate for little r, we know that it's big R times sine theta is equal to little r. Okay, so then we'll equal the two net force x equations together. So Fn sine theta is equal to m little r omega squared, and then we can plug in Fn with what we found earlier, which is mg all over cosine theta all over times sine theta. And then we can replace little r with which we found, which is big R sine theta times omega squared. And then since there's sine theta on both sides, we can cancel those out. And then there's an m on both sides, so we can cancel that out. So you're left with g divided by cosine theta is equal to big R omega squared. And then we can just divide r, so it'd be g all over big R cosine theta is equal to, or let me get rid of that radical real quick, getting ahead of myself. It's equal to omega squared, and then radicalize both sides to solve for omega. So rad g r cosine theta is equal to omega. And that was part H, and that is frq number 4.